Okay, we're going to go ahead and get started with today's lecture. This is going to be on chapter 17 regarding the Earth's interior and seismic waves. Now, how do we know what's inside the Earth? That's been one of the greatest questions for a very long time in geology, is how do we know? Because we can't dig down that far. The deepest mines go down only about 2 miles. And at that point, it is so hot in the earth that it is nearly deadly to be down there for any real length of time. Our deepest borehole has not penetrated the crust of the earth at this point. There was an attempt back in the 60s for what was called the Moho Project to actually drill through the ocean crust and sample the upper mantle. Unfortunately, people convinced Congress this was a bad idea to pull the funding for the project, and they did it with a simple demonstration. They took a water balloon. This is the Earth. Here's a pin. This is the drill. Poke, and well, you know what happens when you poke a water balloon with a pin? It explodes. Congress was actually convinced that yes, if you drill through the crust of the Earth would explode. As dumb as an idea as that is, Congress was convinced of it. So, most of the work that we have used to determine what the interior of the Earth is like is based off of seismic waves. So when we talked about earthquakes last week, or last chapter I should say, we talked about the traveling of the P wave and the S wave through the materials in the Earth, and that P waves will travel through all materials, whereas S waves will travel only through solid materials, and that there is a 1.7 times difference. P waves travel 1.7 times faster than S waves, and knowing that, we can then calculate how things are moving through the Earth. Now, the velocity of seismic waves greatly depends on the nature and specifically the density of the materials that they're traveling through, as well as there is elasticity. The denser and more elastic the materials are, the faster the waves can travel. So generally speaking, within a given layer of the Earth, one of the things that we see is that the speed of the seismic wave actually increases with depth. One of the figures I like for that comes from a different book, and it shows, let's see if I can get this closer without knocking over my drink, this great chart showing the interior of the Earth and then the velocity of the P and S waves. So you can see how they actually increase with depth and decrease, areas where they actually will decrease. This gives us a lot of information about the nature of the interior of the Earth. And by looking for the minute differences in travel times that we expect versus the travel times that we actually observe, depending on where the earthquake or seismic event occurred and where our station is at, allows us to work out what has to have happened in between. Now, can more than one solution give us the same answer? Yes, but generally speaking, we try to keep things to the simplest possible explanation. So, if we, just to review, P waves are compressional. They're like sound waves. They move through solids, liquids, and gases. S waves are shear waves that move side to side, and they only travel through solids. And basically, no matter what the material is, a P wave always travels faster than an S wave. Also, when seismic waves pass from one material to another, we get what's called a refraction event. I'll draw it out here. We see refraction all the time with light, so it's not an uncommon thing that happens. So I'm going to draw a surface here. Let's say that's a surface. Now, the key here for the surface is that the density on one side and the density on the other side to be different. So in this case, let's say D1, D2, where D1 is less than D2, okay? So the density of 1 versus the density of 2, density 1 is less than density 2. If we have an energy wave coming in, whether it's a light wave or a seismic wave, doesn't really matter which one it is, and that energy wave comes into a surface, two things are going to happen at that surface, as long as it's not coming in completely perpendicular to the surface. If it's not completely perpendicular, two things will happen. Some degree of the energy is going to be reflected off, and that reflection is going to happen at the exact same angle that the incident happened, okay? So unless something else is happening here, the angle in is going to equal the angle out for the reflected light or reflected energy. But some of this energy is also going to pass through the boundary, and it's going to bend. And in the case of denser materials, it's going to bend towards the perpendicular. So the energy will bend to try to become more perpendicular to the boundary. Okay? And that is called refraction. Because the angle should have been the same. Had that boundary had no density differences whatsoever, it would have passed through the boundary at the exact same angle in the exact same direction. There would have been some reflection, but there would have been no refraction. So refraction is something that is going to occur. When refraction occurs, that can cause changes in when and where we would expect seismic signals to show up on the Earth. So one of the things that we've seen, as the chart I was holding, or the illustration I was holding up earlier, this one, shows, is that there are rather abrupt changes in different depths in seismic wave velocities. Now, these are going to occur at what we understand to be distinctive layer changes in the Earth. Now, what does this mean in the way we have defined the Earth in terms of its layers? Well, if we go back to what we talked about in chapter 1, we can define the Earth as being made up in layers by two different methods. The first is composition. So, compositionally, the outermost shell of the Earth is the crust, okay? It's thinner than the skin of a peach to a peach in relationship to the Earth. The crust is relatively thin, ranges from 3 to 70 kilometers thick, or basically 2 miles thick to about 40 miles thick. And that's basically going to be from ocean ridge is at its thinnest, under mountains is its thickest. And that's going to be that area. Below the crust, making up the vast majority of the Earth, is the mantle. Okay? The mantle is the second layer. It's basically a rocky shell, although it can move ductily in some areas. It's going to extend down to a depth of about 2,900 kilometers or 1,800 miles, thereabouts. And it is made mostly, we believe, of the mineral peridotite or eclogite, depending on the phase of the material. Chemically speaking, peridotite and eclogite, basically the same thing. The difference is their crystalline structure. And then the interior portion of the Earth, the third layer, is the core. And the core is an iron-rich sphere having a radius of approximately 3,486 kilometers, or 2,161 miles, roughly thereabouts. Okay, those are the layers that we define by composition. So the crust, if you remember the crust, we have the two types of crust: the continental crust, which is felsic in nature, so like granites, or we have the oceanic crust, which is mafic or basaltic in nature. Okay? In terms of the physical property layers, and I'm going to keep bumping my table with my map. One of the things that we look at is that the physical properties also have this issue of dealing with depth as well as temperature. So with increasing temperature, the interior of the Earth has an increasing, with an increasing depth, the Earth has an increasing temperature. So the depth between 100 kilometers is it's going to have a temperature of between 1200 degrees centigrade and 1400 degrees centigrade. Whereas by the time you get to the center of the Earth, the temperature may exceed 6700 degrees centigrade. In fact, technically speaking, the center of the Earth is actually hotter than the physical surface of the sun. Not hotter than the atmosphere of the sun, but the physical surface of the sun. Now, as we go down, the pressure is going to increase. And for the most part, except for where we're dealing with tectonic forces, we're talking about a confining pressure. What this also is going to do is this is going to make the density of material increase. So basically, the deeper you go within the Earth, the greater the density of material becomes. So when we look at this, again, the materials are going to behave based on their conditions that they're in. We can have, going back to when we talked about structural geology with earthquakes, faults and folds, they can behave brittly, they can break and snap, they can deform ductily like a putty, or they can melt and become liquid. So if we go through the main layers, the first layer, the outermost layer, is the lithosphere, which is the outermost layer. It's basically going to be the crust and the uppermost mantle. It helps if I get it into the picture. Do it this way. It's the crust and the uppermost mantle. It's relatively cool. It's rigid. It breaks brittly, so it forms these rigid plates that then move around. Has an average thickness of about 100 kilometers, although under some of the oldest and largest mountains areas, it might get as deep as 250 kilometers, 220, 250 kilometers, somewhere in that ballpark. Basically, this is the active outer shell of the Earth. This is the part that moves around. Below this is the asthenosphere, aka the weak sphere. And this goes down to a depth of about 600 kilometers. Basically what's happening at this point is usually the material is hot enough, it's coming up from a greater depth, and it reaches a point where the pressures are low enough that it induces partial melting. So you have a little bit of melting that's occurring in this layer, and that is enough to partially decouple the outer shell of the Earth from the surface. Now, this doesn't mean that the rest of the Earth is turning underneath the lithosphere. That's been a contention. Some people have taken this bit of knowledge and they've run with it in some weird directions, claiming the surface of the Earth can just slip around and move all over the place instantly, not over time. It's not quite that. It's partially decoupled. It allows it to move slowly, independently of the rest of the Earth. But the cumulative motion is very slow. We're talking inches a year, not feet a second. Okay? But basically it allows the lithosphere to move somewhat independently of the asthenosphere. And this allows for the plates to move and jostle around and create what we call plate tectonics on the Earth. The next layer is the mesosphere, or the lowermost mantle. This is going to be between about 600, 660 kilometers deep to about 2,900 kilometers deep. It's rigid. Generally speaking, it's rigid, though it does flow slowly, ductily over time. Um, the motion is fairly gradual, though we're just beginning to get some really cool animations. You can look them up of mantle convection. They're really cool, that have actually been done using a lot of very detailed seismic telemetry. But basically, the rocks are very hot. Again, they're capable of some degree of motion. It's thick, super viscous type of material, though it still remains and behaves solid in general. Then we have the outer core of the Earth, which starts at about 2,900 kilometers. And if you remember, the core itself is made up of mostly nickel and iron. Roughly 95% iron, 5% nickel. Odds are there's probably some other materials down in there. We'll talk about that in just a minute. But basically, the outer core of the Earth is a layer somewhere in the neighborhood of 2,270 kilometers thick. So 2,270 kilometers thick. It has convective flow within it. It's liquid, so it's just constantly moving. It's hotter at the bottom, cooler at the top, so that means the material is going to move. We believe that convective flow is in large part what creates our magnetic field, so it's very important for life on the Earth. And then the interior part is, of course, the solid core, the solid inner core, which is a sphere that has a radius of about 1,200 kilometers, give or take. The book I've got has always got it wrong. It's, 1,200 and... Yeah, a little over 1,200. I'm not going to get too exact with it right now. But, a little over 1,200, 1,216, I think, kilometers thick. It's crystallized iron nickel. We believe it behaves exactly as we know it behaves like a solid based on our measurements. We believe it's growing over time as the interior of the Earth cools down. The core crystallizes, and that causes the inner core to gradually become larger. One of the things that we also know about the core of the Earth is that the core of the Earth, because the outer core is liquid, the inner core is slightly decoupled from the rest of the Earth, to the point where it is rotating on average 1 degree more every year than the rest of the planet. So if you can think about it this way, if the planet goes through 365 days, technically 365.25 days, but let's round down, 365 days, so the outer surface of the Earth rotates around 365 times. The inner core of the Earth goes 365 and 1/360th more. So over the course of 360 years, the inner core of the Earth makes one more rotation than the outer core or the rest of the Earth. Now, when we figured out that this was happening, one of the first things that was done was they built a scale model of this to try to understand what's happening. This scale model, you can find YouTube videos of this experiment, basically took a iron sphere in the center that had heating elements in it that was on a shaft that could be rotated. Outside of that was another shell with heating elements in it. Now, in order to have a liquid metal in there, they had to use a metal that could melt at a relatively low temperature, but not cause the steel structure to be structurally compromised. So what they used was liquid sodium metal. It melts at a much lower temperature. They fill the sphere with the liquid sodium. They turn the inner sphere on as a heat source. They start spinning the outer sphere and cause the inner sphere to rotate just slightly faster. And almost instantly, a magnetic field very similar to the Earth's magnetic field set up and started evolving within the system. So that gives us a very, very strong indicator that the core of the Earth is generating the magnetic field. Now, the exact mechanisms behind that still remains to be worked out, but nonetheless, we know now that the magnetic field is generated from the core. So what about some of the major boundary levels that are in the Earth, or boundary layers? Let's go through some of those real quick. The first one I want to talk about is probably the hardest one for most people to spell, let alone pronounce. And that's the Mohorovičić. The Mohorovičić, aka the Moho. The Moho boundary, or the Mohorovičić discontinuity, was discovered in 1909 by Andrzeja Mohorovičić. It's a boundary layer that separates the crust from the underlying mantle. It's identified by a change in velocity in the P waves. Okay, so one of the ways we can do this is, remember, there's that refraction that occurs, that bending of the energy as the material goes deeper. In the Earth, it actually causes a curved movement of the energy lines because the density is increasing with depth. So instead of it being a straight boundary, it's causing more of a curve. Because of this, we can actually note when changes happen. So if we look at it from a visual standpoint, and I'm just going to draw this out roughly. If I have something happen here, okay, the path of the energy waves can go like this. Okay, just to kind of illustrate it. So if the energy wave is coming down and just barely missing that boundary, it follows this upper curved surface. But if it just touches that boundary, it's going to divert down and change where it comes out at. So we can see this by looking at the measurements of seismic wave energy and seeing these little spots or shadow zones that are created. Of course, speaking of shadows, the sun keeps going behind the clouds. Okay. Now, the core mantle boundary was discovered in 1914 by Benno Gutenberg. He observed this based on the fact that P waves, generally speaking, will die out 105 degrees away from an earthquake and reappear at about 140 degrees, and about 2 minutes later than expected. This 35-degree belt is now what we refer to as the P wave shadow zone. What this is again this idea of this energy just kissing the boundary. At 105 degrees away from an earthquake, the energy from that earthquake is just barely missing the core mantle boundary. But the next little bit down hits that boundary and gets refracted so that it doesn't come out until 140 degrees away. So this creates this belt on the Earth. Let's see, I believe... Yeah. Page 418 in your book. And I'll turn it so it gets more sun. So there you can see where the energy of the P wave is just missing the core mantle boundary and goes out to 105. That which impinges on the core mantle boundary gets refracted and ends up at 140 degrees. So it creates this, this says 142 now, and this says 103. All right. Changes in textbooks. So this creates this shadow zone. So we can see the shadowed zone, and that gives us the idea that there's a major boundary of some sort within the interior of the Earth, and that, of course, is the core mantle boundary. The other thing that we note with that boundary is that same angular distance, 105, 103, depending on the book you're using, I guess. You don't see any S waves after that. It's a complete S wave shadow zone. So S waves do not make it through that core boundary at all. So that told us that not only is there a boundary layer there, but that boundary had to be one between a solid and a liquid material, because the only reason we don't see S waves is that they hit a liquid material. And then in 1936 came the discovery of the inner core boundary. This was done by Inga Lehman. She was a seismologist who looked at it and found that there was an area within the within the P wave that comes through. There was an area where the P waves are actually appearing just slightly before they should have. Enough where it was determined that, and what she determined was that there must be a solid inner core because of the increase in velocity. The only thing to increase the velocity is going to be the nature of the material. P waves will travel faster in a solid than they will in a liquid. So if you have a solid suspended in that liquid, then you're going to get this increase in velocity. And therefore the P waves are showing up in the antipodal areas, the opposite side of the Earth, 180 degrees or thereabouts, faster than they should otherwise be, by a few seconds, but still faster. So just to kind of go back over it real brief, again, the crust of the Earth is the thickness varies from anywhere from 70 kilometers thick down to 3 kilometers thick on average. Here, under us, right here, care to guess? No, 5. Okay, whoever said 5, you're about correct. The crust under our feet is about 5 kilometers thick. And this is in part because the area below us was pulled apart during this the stretching event that created the basin and range in southern Arizona. The crust was thinned by about 50%. Now, the average density of continental crust is going to be about 2.7 grams per cubic centimeter. Generally speaking, we can find rocks in the continents that exceed 4 billion years old. Generally speaking, their composition is like a granite to a granodiorite. The ocean crust is denser. It's about 3 grams per cubic centimeter. So if you look at it from a mathematical standpoint, it's the density difference between continental material and oceanic material is the same as the density difference between ice and water. This is why the continents sit up so much higher than the ocean basins. Generally speaking, the ocean basins are much, much younger. The oldest material in the ocean basins that we can find is roughly 180 million years old. So this means that the oceans are not only younger, but they're also very active, getting back to the whole idea about plate tectonics, which we will be talking about finally in more detail. The mantle is 82% of the Earth by volume, making it the largest layer there is. It's solid, tends to be rocky, made up of ultramafic rock peridotite in the upper portion. The bottom portion is probably eclogite, which is again just a same general composition, just a different crystalline structure because of the pressure. It has the 2 parts in the lower mantle, which we have not really talked about too much. We have the mesosphere, which is generally the lower mantle in general, with the asthenosphere taking up most of the upper mantle. The mesosphere is basically from the core mantle boundary. It One of the minerals that might be abundant down there is a mineral called perovskite. I'm not terribly familiar with it, but it might be another phase change issue for olivine. But in the bottom 200 kilometers of the mantle is a layer that we call the D layer. This appears to show a sharp decrease in P wave velocities. What we think is happening is the boundary layer is probably not a sharp layer. One of the reasons we think this is meteorites. One of the types of meteorites that we can find on the Earth today are the, and I just lost it, the Palisades. I believe is the right, the Palisades. When you cut a Palisade meteorite and polish it, if you cut it into thin slabs, what you end up with are metal structures with crystalline rock, usually clearish green crystalline rock in between. The crystalline green is usually olivine, and the metal is usually iron nickel. So what we think is happening at the Earth might be based on some of these meteorites, is that the boundary layer between the outer core and the mantle is not, or the mesosphere, is not a very clean layer. It's got pockets of liquid metal that are surrounded by solid rock. And this is what's going to cause the decrease in the P wave velocities. And then, of course, the asthenosphere, which is the upper part that is molten. And then down to the core, generally speaking, keep this in mind. The core of the Earth is actually larger than the planet Mars. It's basically got the two outer parts, the inner core and the outer core, with the outer core being the liquid layer that's approximately 2,270 kilometers thick, and the inner core, which has a radius of about 1,216 kilometers. Generally speaking, the average density of the core system itself is around 11 grams per cubic centimeter. So we're almost four times denser than oceanic crust to begin with. We think that it goes down to a density, or up to a density of 14 grams per cubic centimeter in the inner core. Generally speaking, we believe the core, inner core, outer core, both to be about 95% iron, 5% nickel. There is a small community of geologists, very small, might even be only a handful, who believe that there is an inner core. Now, this is a somewhat reasonable hypothesis. If you go back and think about when we talked about the Earth collecting together with the impact events that were bringing more material into the Earth and heating it up, that we got to a point where we had that segregation of materials by density. So the denser materials migrated towards the center, and the lighter materials migrated towards the outside. Iron is not the densest material. Uranium is much denser than the iron is. Gold is denser. So there is a hypothesis out there that there might be an inner core, and maybe that inner core may have actually been a nuclear pile of some sort, mostly uranium and other heavy metals that are radioactive, that went through a meltdown phase, and that helped to heat up the interior of the Earth. It's possible. To date, nobody's gotten any really solid evidence that would show that it is realistically probable, but it's an interesting idea to at least banty about to some degree. In terms of the origin of the core, basically the explanation that we generally accept is that as the Earth was heating up through bombardment and radioactive decay, basically the denser materials gravitationally went down and lighter materials went out. As it began to cool and crystallize, then we began to get the interior core forming. I already touched on the magnetic field. Again, going back to this idea that it's very hot in the interior of the Earth and rather cool and comfortable on the exterior, gets back to the idea that Earth materials are a poor conductor of heat. This is why we have a geothermal gradient. So generally speaking, for every kilometer you go down into the Earth, the temperature is going to increase between 20 and 30 degrees centigrade. So it can get very hot very quick. 3 degrees centigrade, or 3 kilometers down, you're going to be starting to get close to average temperatures of near 100 degrees centigrade, or nearly the boiling point of water. In fact, the deepest mine in South Africa, which is the deepest mine in the world, going down almost 2 miles deep, has an average air temperature, if I remember correctly, average wall temperature is 180 to 185 degrees Fahrenheit. It's a steam bath, basically, and people can only work down there a couple of hours at a time max. Generally speaking, where does the heat come from? We have the latent heat of formation that was left over, plus radioactive decay, namely uranium, thorium, and potassium isotopes. There's all sorts of different sources of heat, other radioactive materials that are probably less abundant, but they still are going to provide some small little kick of heat. But basically, we have to remember that in the interior of the Earth, heat can only move basically in one of two ways. Heat can travel, and energy travels in 3 ways in our atmosphere. It can travel through radiation. Step outside, feel the heat from the sun. That's heat that has traveled through the vacuum of space. No medium of transmission is needed. The other is convection. Easiest way to explain convection: you're cooking something in the oven. You open the oven up. You get that rush of hot air that comes up and hits you in the face. That's convection. That's heat moving from one location to another under a density force, basically. And then finally is conduction. The easiest way I can explain conduction is you're making a pot of chili or menudo or pozole or whatever, and you got it on the stove. You go to stir it. You stick the spoon in there and you start stirring it. Now, thinking that you're not going to be leaving the spoon in there, you use a big metal spoon. Phone rings. You go answer the phone call. You're on there. Oh, I need to go stir my pot of whatever. You go grab it, and you left the spoon in there. Now what happens? Yeah, you burnt your hand because the spoon got hot. How did it get hot? It conducted the heat. So conduction. Generally speaking, if there's convection within the Earth, that's moving heat through convection. If otherwise, the heat has to move through conduction. And that's the transfer of energy from molecule to molecule. And it's a very slow process within the Earth. That's why homes that are built out of earthen materials tend to have a high insulation property to them. Finally, mantle convection. I don't want to travel too much or spend too much time on mantle convection. Mantle convection, we know, is occurring to some degree. Your book on page 419 actually has a little bit of a write-up on it. It's interesting. We're just really this is a field of the science that has really only started coming to light in the last 10 years or so. That's really allowing us to see what is happening in the Earth and trying to map out how this material is moving and whatnot. A couple of other things your book talks about that I probably should talk about here. I will mention again when we talk more about mountains, is the idea of isostasy. Isostasy is a really interesting field of interest in geology. It's basically a balance or equilibrium of blocks. The way this works is we take an arbitrary depth below the surface of the Earth, usually down into the mantle. Okay, so we're going to have this arbitrary depth, and we're going to take sea level as another boundary layer. And what we do is we break the Earth up into block units, or columns, if you will. So I'm going to draw this out. Now the idea is that every column down to this arbitrary depth is going to be roughly the same size in terms of its width. So every column is roughly the same width. So every column would have the same surface area. Now, I'm not drawing it out that way, but it's because I'm trying to do it freehand and my elbow is now killing me. Now, the other thing in this is we make an assumption with isostasy. And the assumption is that the mass in every single one of these columns, which I'll show you here in a second, is going to be exactly the same. So I'm just going to label these columns as C1, C2, so forth and so on. So I got 8 of them. So the idea is that the columns are also going to be made up of different materials. So let me show you what I've got here. So I got 8 columns. Okay, again, it's just an arbitrary depth down into the earth. And I have sea level up here as my upper layer. I've got these columns in the Earth's crust. Okay, let's just, for the sake of argument, say they're equidimensional in terms of their width. Not in their height, but just their width. So what the difference is in this is that the density in these columns has differences in it. So we have the upper material and the lower material. The upper material is going to be less dense material, and the lower material is going to be more dense material. So if a column is supposed to have the exact same amount of mass in it, then the volume of materials has to change in order for that to happen. So if I take a less dense material, let's say feathers, and I want to have 100 pounds of feathers, it's going to take a very large volume of feathers to get to that tonnage, or that poundage. If I want a denser material, let's say lead, it's not going to take a lot of lead for me to get to 100 pounds. So volumetrically, there's a lot less lead to feathers in terms of the total volume. So that's what's happening here. This is what we're assuming is happening with the Earth's crust, is that every unit has different materials of different densities in it, but it's the volume of those materials that give us this mass idea. So the idea then becomes is that if each of these columns is basically floating on the Earth, if you will, and we do something to one of these columns to change it in some way, shape, or form, that's going to have an effect on where it wants to sit. So if I take, for example, and I add more lighter material onto this column here, the net effect is this column is going to want to decrease downwards. It's going to want to go down. If I then, at some point, once it's made that adjustment, remove that material, then that column is going to revert back upwards to its original height. This is what we call isostatic adjustments or isostatic rebound. Remember, when we talked about glaciers, I talked about how some of the land around the Great Lakes is rebounding. It's moving upwards at a rate of a fraction of an inch every century. This is because when we had the last ice age, the weight of the glaciers in the area pressed down, and the whole column of earth under it sank in relationship to that weight. Now that the glaciers have melted off, those columns are now rising back up, just trying to find their isostatic equilibrium. This actually helps us understand events that happen with mountains. One of the things that we see with mountains, and your book shows a pretty good display on this on 222, is when we have a mountain, it tends to have a deep root to it. But as the mountain weathers, we see the mountain rising up. And as it continues to weather, we weather deeper and deeper into it. This is why in the areas of the continent where we see the remains of the oldest mountains, we see the root of the mountains. We don't see the tops or the middles of the mountains. We see the bottom root because that material has come back up and been weathered away. We can also do gravity measurements from seismic activities, magnetic measurements. I'm not going to get into too much of these because realistically speaking, it goes beyond what you really need to know for this course. I will mention magnetic reversals once again. We're going to talk about this more when we talk about the sea floor in the next chapter. But certain rocks, especially basalts, can record the magnetic field of the earth at the time that those rocks cool and solidify. And so what we see is that from time to time, there will be a point in time, whether it's in your lifetime or not, there will be a point in time where you could walk outside with a magnetic compass and north will not be pointing on that compass to the north, it will be pointing towards Mexico. And that's because of a magnetic reversal. The magnetic field of the earth reverses from time to time. Why? We don't know. It just does. But we can make those studies as well as gravitational studies. And we can find anomalies in the gravitational field or in the magnetic field that can be related to different structures in the earth, different materials within the earth. There's really a large degree of science around that. But I'm going to go ahead and cut this off here so I keep the video relatively easy to watch in one sitting. Again, when we talk about this tonight or next time, feel free to ask questions if you don't understand something. Feel free to email me if you don't understand something. And with that, I'll talk to you guys later. Have a good one.